let f of x equal 1 plus x to the power p, where p is some real number, p is a real number. Let's show that the Maclaurin series for 1 plus x to the p is the sum from n equals 0 to infinity of p times p minus 1 times p minus 2 times p minus 3 times so on, all the way up to p minus n plus 1 times x to the n over n factorial. That's part A. Part B, we need to find the radius of convergence, so that's usually a lot easier than finding the interval of convergence. And part C, for x between 0 and 1, including 0 but not including 1, use the remainder term, so write this Lagrange error term to show that 1 plus x to the p equals its Maclaurin series. So that tends to be quite difficult. It's algebraically quite demanding, but we'll see how we get on. So firstly, if you're doing a Maclaurin series, we start in the same way with f of x. Remember, for a Maclaurin series, we need f of 0, f dash 0, f dash dash 0, and so on. Look to find a pattern and then try to define it as the nth derivative. And we're going to need the n plus 1th derivative as well if we're going to do the error term. And also, once we're finding the radius of convergence, if we're going to use the ratio test, we're going to need the n plus 1th derivative for that as well. So f of x equals 1 plus x to the p. F of 0, well, that's going to be 1 plus 0 to the power p, which is going to be 1 to the power p. So 1 to the power of some real number is just going to be 1. F dashed x, simple enough derivative, you bring the power to the front, so that's going to be p times the bit in the bracket, 1 plus x to the power of p minus 1, we drop the power by 1, and then times the derivative of the bit in the bracket, which is just 1, so it doesn't do anything. So f dash 0 is going to be, well, it's p times 1 plus 0 to the power p minus 1. Well, 1 plus 0 is just 1. 1 to the power p minus 1 will still be 1. So it's just p. F dashed x. Well, that is going to be, remember, powers to the front. So it's p times p minus 1 times 1 plus x to the power p minus 2 times the derivative of the bit in the bracket, which is just 1. And f dash 0 equals, well, it's p times p minus 1 times 1, because 1 plus 0 is just 1. 1 to the power p minus 2 is 1. So it's going to be p times p minus 1. And now there should be enough to see a pattern. So f dash x is going to be p minus 1, p minus 2, 1 plus x to the power p minus 3. And so f dash 0 is going to be p minus 1, p minus 2. Okay, so now looking at what's going on, we've done the third derivative without having to actually do the chain rule differentiation. So that should be enough to do a bit of pattern spotting. So the nth derivative of x, well, you've got all these p's being times together. So you're going to have sort of p times p minus 1 times p minus 2 and so on, all the way up to, now you've got to decide where it goes to. Well, it's always 1 less than n, isn't it? Because if for the third derivative, we went up to p minus 2. For the second derivative, we went up to p minus 1 and so on. So this is going to go, for the nth derivative, it's going to go up to p minus n minus 1. So p minus n minus 1. So that's the p bit, and then you're going to have some power of 1 plus x. And you think of the power, well, that is p minus n, because for the third derivative, it's p minus 3. For the second derivative, p minus 2. So this is going to be p minus n. Okay, we can tidy that up a bit. If we look at this p minus n minus 1 term, well, if we just remove that second bracket, that would be p minus n plus 1. So the nth derivative of x is going to be p minus 1, p minus 2, and so on, all being multiplied together up to p minus n plus 1 times 1 plus x to the power p minus n. Right, so if we evaluate this thing at 0, the nth derivative at 0, which we are going to need for our expansion, where it's going to be all those p's, and just think about how everything else went. This final bit, the 1 plus x to the p minus n, is just going to be 1. So that is just going to leave you p minus 1, p minus 2, dot, 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 up into p minus n plus 1. So that is the nth derivative evaluated at 0. Now we're going to need the n plus 1th derivative, so one more. And if you just think about differentiating this thing, this p minus n is going to come into here. And the power is going to drop by 1. So the power is going to be p minus n minus 1. And not much else is going to change. So the n plus 1th derivative of x is going to be what? p minus 1, p minus 2, dot, dot, dot. We'll include the p minus n plus 1. Then we've got this one more power, which is this green bit. So then you've got p minus n. Remember, that's coming in as a multiplier when we differentiate. And then we've still got our 1 plus x, and we drop the power by 1, so we said it was p minus n minus 1. Okay, it's a very useful expression, and we're really going to need that at 0 and at c later on for the error term, so I'm just going to do them both now. And the n plus 1th derivative evaluated at 0 is going to be p minus 1, p minus 2, dot, 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 p minus n plus 1, p minus n, and the 1 plus x to the power of p minus n minus 1 disappears because it's 1 plus 0, which is 1, and then 1 to the power of p minus n minus 1 is just 1. Okay, if we evaluate the thing at c, so the n plus 1th derivative evaluated at c, which we will use later, is going to be p minus 1, p minus 2, dot, 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 p minus n plus 1, p minus n, and obviously you've now got 1 plus c. 1 plus c to the power of p minus n minus 1. Okay, I'm just going to highlight some of these useful results because we're definitely going to use them again. So we definitely want to use that nth derivative at 0. We definitely are going to use the n plus 1th derivative at 0. That's going to be used in the ratio test part. And we're going to use the n plus 1th derivative evaluated at c. That is going to be used when we are showing that the limit has then approached infinity of the error term equals 0. So now we can write out a bit of this Maclaurin series. We have all the information. We have f0, we have f dash 0, we have f dash dash 0, and so on. So now f of x equals f0, which is 1, plus f dash 0x, which is px, plus f dashed 0 times x squared over 2 factorial, which is p minus 1 times x squared over 2 factorial, plus dot, dot, dot. So we're going to, obviously the next term would be p minus 1, p minus 2, x cubed over 3 factorial, and so on. but we're going to go up to the end, which is p minus 1, p minus 2, and so on, dot, 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 all the way up to, remember, p minus n plus 1, and it's going to be x to the n over n factorial. So that is our series, plus, if I can just squeeze it in, plus our Rn x. And it's exact. So to define this using series notation, f of x is going to be some kind of series. Look at the powers. We've got 1 as the first term. That's x to the power 0, x to the power 1, x to the power 2, and so on. They're all there. So we're going to start from n equals 0 all the way up to infinity. And it is, so you've always got your p times p minus 1 times dot, 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 times p minus n plus 1. So all of these times x to the n over n factorial. Obviously, when n is 0, you've got a 1 here. So you've kind of got a 1 dot, which, yes, if n is 0, you're going to have 1 times x to the 0 over 0 factorial, which is where you get your 1 from. Then when x is 1, you're going to have p, or 1 times p times x to the 1 over 1 factorial. That's where you get your px from. And so there is a 1 here, but the reason why it's the same, just because this 1, if you have 1 times something, it doesn't actually do anything. So I've been asked to express it without this 1, so we're going to remove it like that. Okay, find the associated radius of convergence. So I will label what question that was. I do have a bad habit with these long questions of not labeling the parts. So part B, we need to find the radius, not the interval, of convergence. So whenever you are looking for a radius or an interval of convergence of a power series, you start in the same way. And we are going to use the ratio test, which means we find the limit as n approaches infinity of the absolute value of a, n plus 1 over a to the n. So now we need an expression for a n plus 1. We're quite lucky that we actually have it. So for our expression for a n plus 1, that is why this particular term is so useful, because a n plus 1, well, it's going to be the n plus 1th derivative evaluated at 0. So we already have that. It's all of these p terms being times together up to and including p minus n. And then we just need to increase the power of x by 1, so x to the n plus 1 over n plus 1 factorial. So we need to find the lim as n approaches infinity of, well, it's p minus 1, p minus 2, dot, 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 p minus n plus 1, p minus n, all of that, times x to the n plus 1 over n plus 1 factorial. So that is the a n plus 1 term, all over the a n term, which we already have, which is p minus 1, p minus 2, dot, 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 p minus n plus 1. We stopped there, and it was x to the n over n factorial, and it's the absolute value of all of that. So then we do our usual simplifications. X to the n plus 1 is x times x to the n. So this now equals the lim as n approaches infinity of p minus 1, p minus 2, dot, 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 p minus n plus 1, p minus n. So we've got x to the n plus 1, which is x times x to the n, all over n plus 1 factorial, which we're going to write as n plus 1 times n factorial. Okay, and if we're dividing by a fraction, we can multiply it by its reciprocal. So that means Well, on the top, we're just going to have n factorial. And on the bottom, we've got all of this p minus 1, p minus 2, and so on. P minus 1, p minus 2, p minus n plus 1, and you've got x to the n. And we need the absolute value of all of that. So, looking at the cancellation, as always, it's very friendly. Take the n factorial with the n factorial, 1, 1. X to the n with the x to the n, 1, 1. And then you've got all of these powers of p up into p minus n plus 1. They also cancel off. So now we're left with the lim as n approaches infinity of the absolute value of p minus n x over n plus 1. Now, in a lot of these ratio tests, we've said that the negative bit can come from the x. In this particular case, because you know n's approaching infinity, on the top there you've got a p minus n, so that could potentially give you a negative as well. So we can pull the x out because x isn't affected by a limit in n, as in n approaches infinity doesn't change x, it only changes n. But we can't have that as the only bit of the absolute. So we're going to say this is the absolute value of x times the lim as n approaches infinity of the absolute value of, well, you've got p minus n on the top over n. So I'm going to just divide everything through by n. So p over n minus n over n over n over n plus 1 over n. So that gives us the absolute value of x times, well, here now you have the absolute value of p minus n. Well, p is just a real number. So if n's approaching infinity, that's going to be 0 minus n over n is 1 over, and then n over n again, 1 plus 1 over n, we know approaches 0 as n approaches infinity. So that is the absolute value of x times the absolute value of minus 1 over 1, which is minus 1, equals the absolute value of x. So that's the result of the ratio test. And remember that the ratio test converges. So series converges when the value of the ratio test is less than 1. So when the absolute value of x is less than 1, and remember that now is our radius of convergence. We've only been asked for the radius of convergence. Okay, the way I've described it before, we know that if we've got x between minus 1 and 1, so anywhere in there, the ratio test will give a value less than 1, and so it will converge. So if you think about the width of that, minus 1 and 1, we know it converges all the way in there, and the radius of convergence is half of that, right? So these distances here are the radius of convergence. And it's just 1 because this distance is 2. So radius of convergence is 1. Okay, so part C, for x between 0 and 1, including 0, not including 1, use the remainder term to show that 1 plus x to the p equals its Maclaurin series. And you do that by showing that the limits as x approaches 0 of the absolute value. You do that by showing that the limits as n approaches infinity of the absolute value of the error term equals 0. So that means that the actual, once you have more and more and more terms, as you get to a massive amount of terms, the series and the actual sequence it represents are indistinguishable. So I've just brought all the information we're going to need. Firstly, this is obviously from the formula book, the Lagrange form. So we have the error term is the n plus 1th derivative evaluated at c. X minus a, remember this is a Taylor series thing in the formula book, a is just 0, so it's x to the n plus 1, so the next power of x over n plus 1 factorial. We already have our n plus 1th derivative evaluated at c, which is quite handy, and we already have this series as well, so we're just going to put everything together, and it's just going to be x to the n plus 1 over n plus 1 factorial. So the error term equals, so it's the n plus 1 derivative evaluated at c, so it's p minus 1, p minus 2, p minus n plus 1, p minus n times 1 plus c to the power p minus n minus 1 times x to the n plus 1 all over n plus 1 factorial. So the key to this is to think about, can we represent this in a different way? Because you're looking at its n. Remember, n's getting really big, but the p is obviously just a constant real number, and minus 1 is obviously just minus 1. So if we can just rewrite this power, that is the key. So basically, 1 plus c to the power of p minus n minus 1 could be written as 1 plus c to the power of p minus 1 divided by 1 plus c to the power of n. Just think about that. Using simple laws, it would be 1 plus c to the power of p minus 1 minus n. So exactly the same thing. And we're interested in, we want to get really big numbers on the bottom. We're hoping for it to get to a 0. So we're going to use this other form. So now the error term Rnx can be written as p minus 1 all the way up to p minus n x to the power n plus 1 over n plus 1 factorial times 1 plus c to the p minus 1 over 1 plus c to the n. And don't forget that you have c needs to be between 0 and x, and x needs to be greater than or equal to 0 but less than 1. So now we can pull this bit out as a constant. It's got no n's in there, so it doesn't need to be included in the limit term. It's just 1 plus c, c is just a number. Power p minus 1, p is also just a number. So now the error term Rnx equals, well, it's that constant, 1 plus c to the power p minus 1. Now we can deal with the two limits of the two bits, so times the lim as n approaches infinity of p minus 1 p minus n x to the n plus 1 over n plus 1 factorial times the lim as n approaches infinity of 1 over 1 plus c to the n. So this first bit is just a nice constant. If we look at this second limit, well, the key is knowing that x needs to be between 0 and 1. Basically, if x is between 0 and 1, so this bit here, so as n approaches infinity, x to the power n plus 1, well, it's going to approach 0 as x is in here. Okay, so because we know x is 0.00 something or 0 point something, once you raise it to a massive power, it's going to get very, very close to 0. So then this whole limit, we basically got 0 over infinity, so that's going to be 0. And if you look at the second limit, because we know that c also needs to be between 0 and 1, so that 1 plus c is going to be bigger than 1, which means that 1 plus c to the n is going to be gigantic, and 1 over that is going to be very, very close to 0. So we have, finally, this equals 1 plus c to the p minus 1, just a constant, times the result of this limit, which is 0, times the result of this limit, which is also 0. So that means the lim as n approaches infinity of the error term equals 0, and f of x equals 1 plus x to the p equals exactly the sum from n equals 0 to infinity of p minus 1 dot 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 p minus n plus 1 x to the n over n factorial, as long as the absolute value of x is less than 1. And now that we've gotten to the end, it's time to tell you this is an incredibly important result. So it's the binomial series for when the absolute value of x is less than 1. It's a standard result. You won't find it in your formula book, but it might be something that you can remember and use when the time comes.